And we're right back. Boom. Oh, I haven't been anywhere. It's my third Space Tour Truck video of the day. And it's probably going to be the last one I ever make, perhaps. We're about to find out. Let's go. 7.25. Let's review what you have learned. Alright. Alright, I'm ready. This... Oh. So we have acceleration in a black hole. Oh, no. So, this looks fine. And then... But we need that to be a black hole. So this is acceleration and this is the black hole, right? So we want the black hole to appear at -10. 0. And we're going to do half a turn on it. The radius is 15. Half a turn. Let's say 4.71 seconds. Let's say we're going at, 10. We'll see. We might have to change that. In fact, do we have to change that? Because if we're going here with the acceleration, what is this? This is 0, 9, 16. That one is very familiar. Where are we? 9, 16, 21. Okay, so -2, and that's going to be... Where do we get to with that? That's 16, and then it's 21, and then it's 24, 25. That seems weird. 21, 24, 25. Yep, so -2. It's going to be 5 seconds to get to here. So actually, 5 seconds. And that's going to be -2 on the... Where are we going? We're going -y. And then... Our initial position is going to be 0, 25. And initial velocity... We need to be going... across the X. And this is going to careen down here. And that's going to be 5 seconds. That's going to be 1, 2, 3, 4, 5. Yep. So that's good. And then, after that, we're going to get pulled in by this black hole. And we need another 9 seconds there. So we were correct. This is actually going to be a speed of 5. So good job we did that testing first. Did the other side first. This is the radius 15, 5, 9.42. And the power of that is 15, 5 is 1.67. And that should about do this. We missed that one. Why did we miss that one? I'm very lost now. What happened? That was strange. We went from 0 to 9 to 15. Oh, we didn't do anything with the Y, did we? In the Y-axis. We actually need to go negatively 10. Y-axis also. Don't we? Excuse me, 1 second. Oh, positively. And wait. We got negatively at -10, and then we need -2. No. Here, +2. Actually, no, that's the wrong way. We're doing that the wrong way. Come here. The 5 changes... X9. We're doing it on the X-axis. Why am I doing it on the Y-axis? The Y-axis is the same. The Y-axis is just 1, 2, 3... The Y-axis is 25, 20, 15, 10, 5, 0. So... That's 1, 2, 3, 4, 5, 6 seconds, I guess. 1, 2, 3, 4, 5. No. 1, 2, 3, 4, 5. 5, and that's going at -5. And this needs to be going -10. I am a fool. Here we go. What have I done? Negative, dude. Negative. Negative Y. Come on. Excuse me. For 5 seconds. And we should end up... So, -2 for 5 seconds on... No, where is it? Oh, it's +2. We've got negative 9, 16. Because that's what we're peeling away from, right? We're going this way at 10. This way at negative 5, yeah. And then we need to go... at negative 2. I've gone off to the wrong side again. What am I doing? We're curling around this way. We need to peel off the positive 2. What is wrong with me? It's totally useless with the acceleration right now. It's because we haven't done it in a little while. It wasn't challenging. I'm confusing which, the X and Y axis, which one I'm, kind of peeling off of with the acceleration. Oh, we did it. That's, Krista McAuliffe. She's one of 2 female astronauts who died in the Space Shuttle Challenger disaster in 1986. As a teacher, she would have been the first civilian to go to space. Ooh. She was recruited by NASA through the Teacher in Space program. This program was to inspire students, honor teachers, and stimulate young people's interest in science and technology. NASA has been severely criticized and accused by many of neglect for the Space Shuttle Challenger crash. Oh, that's awful. Awful. Another black hole. And another acceleration. This here seems like a black hole, like a quarter. But I don't see why we need an acceleration. Where is this? This is 15 and this is 20. I can't do that. It's got to be here, right? So maybe this is the acceleration. I don't... Oh, this is weird. Initial position. We have to start at 0, 0. Ah. And we have to accelerate first. So we're going to go up and then back down. And then go into the black hole. So let's do the black hole first. It's going to be at 20, 0. We are going to be going... positive Y, 10. And then if we go here, and if we do, we want to go back to 2 in a couple of seconds. So minus 10 on the Y. 2 seconds. Go back to 0. And then at 2 seconds, we want to have the black hole appear there, and that's a radius of 20, and we're going to be going at 10. So 2010, 6.67 strength here, and that should do it. But is this going to reach us before we start getting pulled backwards? No. Yeah, that does seem weird, right? This is like 15. 15. I feel like this is what happens and it pulls us slowly here. I think like it actually needs to go here. I feel like that's where the black hole should go. And it doesn't get us until another extra second, basically. Or 2.5. Because it's an extra half. Okay. So if we look at this again. This is, oh no, wait. We're going positive Y, 10. And then we want to get back to 0 in a couple of seconds. 5 seconds way too slow. We want to go back to minus 5. Can we do that? We can go back to 5. Yeah, no. Minus 6 in 3 seconds. Minus 6 could do it. So if we put this as minus 8. Let me try this. We're not going to hit that. Yeah, that always confused me, did that one. But that's also not correct. Okay, this one's tricky. I think this is what we need to do, though. We need to go up here and then back down for the black hole to pull us across. Maybe the black hole does need to be here. But no. Here seems correct. Maybe it does need to be a little lower. Because the curve is here, I guess, and it's pulling us across. 20 minus 10. This is, I do feel like this is a little bit trial and error as well. But we don't be going 15 speed. We're going quarter there, 15 speed. At a radius of what, 10? 1 second? Okay, yeah. So if we go minus 6, we're going to go back to 3 and then negative 8, which is about right, in 4 seconds. So we want to do this in like 3.5 seconds. Oh, not fast enough. Not fast enough. Do we want to do this at 15? Do we want to actually do this at 15? Because this is it's going to change these calculations, obviously, so I don't know if we can do that. Let's try. And then this is going to be minus 8 to go to minus 6 in 3 seconds. Oh, but that's going to be... It's not, is it? It's going to be... Because we're going faster, it's going to take way longer to get there. We just need to try this now. Yeah, we're going to go too far up. It's going to shoot us down. Oh, yeah. And I don't think we would have hit that anyway, yeah. Too fast. That gravity would need to be stronger, probably. Yeah. So I think we have to go 10. We have to go 3 seconds. We go minus 8, it takes us to... So we go 6, but we actually need to reach 10. We actually need to reach 10, right? So if we do it at minus 6, but we're going at 15, is that what we just did? In 3 seconds, we're back at 3. In 4 seconds, we're back at minus 8, and yeah, and then we only have 1 second. That's what we just did, I think. Whoa, that took us up to like 18. Whoa, and then sucked us into the black hole. That were awesome. I do have an issue with this. This is hard. What we want to do is, in a couple of seconds, we need to go minus 4. We could go 8, 12, 12, 8, 0. That's 5 seconds. That's everything we have. What does this one do? Still too high. Still too high, but if we did that for a little bit longer, that seems like it could actually shoot us across the right way. Isn't this what we already did, though? 3.5 is about correct. Oh my god. Oh my god, we were right there. We were right there. That was just crazy. I do feel like it's taking some track. That, I mean, if we could cut some time off there, would be solid. But yeah, 3.5. Cut some time off, but this isn't. This is too strong? The minus 10. No, we're actually okay with the minus 10. But that needs to be 3 seconds. So if we do minus 10, let me look at this. Do minus 10 in 3 seconds. We're at minus 15. But if we do it at 15, so it should be, this should only be 7.5 though, right? Or I don't know how it works like that. But clearly it works. We do get to like quite high. Okay. And then maybe we want stronger gravity. I feel like this one wants trial and error, you know what I mean? Like this one's the same. Shouldn't this also be like 15 though? Let's just try with this one. But I feel like it should be 15. Because we're going at 15 speed. Yeah. 100%. But, yeah, the 15 makes sense to me. This part here. No, maybe 20? But this acceleration is very confusing because we need to do 1.5 at 15. Oh, it's not enough. It's not enough. It's not enough. Maybe we actually do need it to be at negative 20. Sorry, at 0. Where does it appear? Maybe if it's negative 5 instead. And it's 15. It's a radius of 15. Oh, what? Damn it. I think that's not going to be good enough, though. Oh, it is. So let's work backwards on that one. I kind of want to go through that one again and see what we did. Let's see. I want to go back. I want to go back to the solved answer real quick. So we want to go positive 15. For 3 seconds, we're going negative 10. Then this is going to appear at 20, negative 5 with a force of 11.25. I'll stop it just before it finishes, just to make sure this is what we did. Yes. So, let's look at what we did first here. This is why it was tricky, because these calculations are based on if you have 10, you're going at a speed of 10, but we're going at a speed of 15. So what we had to do is kind of guess that this was going to let us reach our speed before it started pulling us back. And it does. It kind of gets us to about 12. It gets us to about 12 before we're getting pulled back. But then after 3 seconds, because we got further away, we don't get to minus 15. We're actually getting way less than that. We're actually getting to about minus 5 or 6. Then, in fact, where are we getting? In 3 seconds? Yeah, we're getting to about minus 5 just. Maybe minus 4. Then the black hole, that one's simple, because this one is just a normal curve of a radius of 15 with 15 speed. 15 is 15. So but then because we actually need to like curve into it from further away, the 15 pulled us off the course too much, so we just rebalanced it. But this is some trial and error work for sure. This isn't something that we could have just figured out with those graphs. Maybe I'm wrong, but it doesn't feel that way. Here's Judith Resnick. She's one of the 2 female astronauts who died in the Space Shuttle Challenge disaster in 1986. She applied to NASA while she was in the process of completing her doctorate in engineering. She was the 2nd American woman to be in space. Introduction to the link between acceleration, the time, and the velocity. Oh, Jesus. I need more brain juice. A new table. The last table. Our control panel. Okay. What's the difference between? Okay. That's time. Isn't this a... Oh, table, if A is a constant during T, and this is R if A is a constant during T, and the initial velocity is equal to... Okay. Alright. Let's try this out. We have a black hole, which we want to be at minus 1510. And it's a radius of 15. It's a radius of 15. And we only have 14 seconds, so we need it to be 10. We need to be moving at a speed of 10, so we are going to be going a speed of 10. We can't change our initial velocity, actually. We can only accelerate to 10 in time. And then it's going to pull us around. Alright. So we need to accelerate to 10. So this is going to be 10 anyway. This is going to be 10. And the time it's going to take to do a full rotation, 1010 is, 6.28. Okay, so we have about 8 seconds to reach that velocity. So this is that acceleration, which is way too much. So maybe we can't even improve this. So if we over time, and this is what though? Delta V. Delta velocity norm, acceleration norm. So we're accelerating 5 seconds to get to 10 on this. So 5 seconds to get to 10. That's fine. We get here in 5 seconds. But then we want to do a full round and we're going 5 and the radius is 15. This is too slow. So we actually need to maybe get a little bit faster. So if we do it and we get to 20, no. So we get to 10 around this time. That's way cut in half though, isn't it? I think that's what we do though. And how long do we do this for? So this table here, how many seconds do we do this for? Well, 2.5. 2.5, yeah. Exactly there where it reaches 10. 2.5 seconds, we should reach a speed of 10. And then 2.5 seconds, we reach a speed of 10. And then to do this with 10 speed and 15 radius is 9.4 seconds. Okay. Whoa! No. Absolutely not. I mean, I love watching this go crazy, but absolutely not. What happened? Why were we going so slow? I thought we didn't reach a... What is this? What's the output here? This is the time interval. This is the acceleration norm. The delta velocity norm. So 10... What do we do then? In 2.5 seconds... We were at 10. We reached 10, but we're still going very slowly. No, we didn't. We reached like 7.5. Didn't even reach 8. That's because we're not going at the correct speed. We need to be going at 4. Idiot. And then we should reach 10 just as that comes down and pulls us around. We need that black hole there a little faster. No. Okay. Okay. Someone burning incense? I can smell incense. It's very weird. We don't use incense. I don't know who would be. This is strange. This is very strange. I can't... I mean, we could just keep going around that, but... But this is the delta velocity norm. I want to be going at 10. A speed of 10 by the time we reach 10. One second, 10. Let's just... I want to see what this does. Acceleration. Right. So it is about not the distance you reach anymore. It's the velocity. So it's 10 millimeters per second. So we do actually reach 10 meters per second in 1 second. But if I put 2 in 2 seconds... We're just below 5, so we're actually on just on 5 almost. That's 5 at 2.1. So this isn't distance. This is just speed. And what we want to do is we need to get to 10 in a couple of seconds. But this is about speed that we need to get to. And we only have a short area to do it in, though. We can change his initial position. We can change our initial position to get up to speed in time. So if we reach... We need to hit 15, right? So let's say we go 4. And we do that in 4 seconds, right? That's 16. We do that in 4 seconds. So let's say we have 4 seconds to do that. But that's going to be going... The first second you go 4 meters. The second you go 8 meters. Right? So it's going to be like, you have to add all of these up. Is that not correct? 20, 40. So, and we need to get here. So we need to be at like minus 30. When we hit there. And then at 4 seconds, the black hole can do what it needs to do. Is that correct? Wow. That seemed to not be very strong. 1 second. Maybe is the radius wrong on this one? What am I calculating this radius at? This radius is 15. Where is it? Black hole. This radius is 15 and I'm going at 10. 6.67. Oh. Oops. Ah. Speed of 10. Radius 15. 6.67. Oh, wait, is it radius? Wait a minute. Go back. Radius 15. 10. 9.42. That's the time. Yeah, 15, 10, 6.67. But it does actually appear on time, right? So I was correct. You add each one of those up. So at 4 seconds... No, actually, no. At 4 seconds is too early. This is what I don't know the distance that we reach in that time. That's the problem. I added all of these up because we have 4 seconds. And in the first second, you're going 4 meters a second. But you're not. You're accelerating to that amount. So how far behind are we? We're a full, like, 8 below. We're a full, like, 8 below. And at that point, we're going at 16. So if we do 4.5 and do another 8, because we're not accelerating anymore, right? This is killing me a little bit. I think I'm going to jump off this one a second. This isn't the last one, is it? No. This is going to be more of the same though, isn't it? Yeah. Introduction to the link between the acceleration, the time, and the velocity. Here's a new table that shows you a link between the acceleration, the time, and the velocity. That'll be useful. So time, acceleration, and velocity is the output. Let's say, but we need to be going 10. In 2.5 seconds at 4. In 2.5 seconds, we should be going 10. If we start at 0, 0. No, if we start 0, 0, that doesn't matter. This black hole needs to start at negative 15, 10. And it needs to have a gravitational pull of 10, right? Because we're going to be going 10. 10, 10, 10. Here we go. And then 10, 10, 6.28. Maybe that's not enough. Maybe it needs to be 10, 5, right? 12.27. But we have to also think of the how many seconds? The 2.5 seconds. So, yeah. 2.5 seconds on top of this is too slow. That's 15 seconds. So we'll do it with this. 6.28. Which is fast. It doesn't matter because they'll just keep going around anyway, right? and 10. But the thing is, so this 2.5, you can see this is going 4, 8, 12, 16, right? So at 2.5 seconds, this should be 10. That's the delta velocity norm. But we don't know the distance that it has traveled in that time. One second at 10. Is just... In 1 second, it should be at 10. The speed of 10, but it hasn't reached 10 yet. How do we know when it reaches something? That's the concern. Because this is whatever. But the black hole, I need to be exactly on with when it starts pulling us in. That's what I'm not understanding from this graph. It doesn't seem to teach me that. The time, the acceleration, so if we do, I don't know, yeah, let's just do 3 seconds of 4. And that says 4, 8, 12. And then in 3 seconds, we're way off. We started accelerating. I'm going to look. Since the initial velocity is fixed and 0, the vehicle will have to be accelerated that it can reach a velocity that will make it allowed to make circular movement. Yes. In the table on page 15, find the acceleration that allows the vehicle to reach a velocity of 5, 10, or 15. Memorize the time required, the chosen velocity. No, we know that. We know this. I understand this. But the 5, 10, or 15, I mean, we could do it here, right, at 10, which is what we did the first time. So, I mean, we go back to 2, and you do this for 5 seconds, and that's reaching 10. But then, how do we calculate the distance of that? On page 5 of the instruction manual, acceleration, find the displacement acceleration. Is that the same thing, though? The displacement? So 5 seconds at what? This acceleration goes 25? Is that the same thing? So if I go up minus 15, this should line up perfectly. Is that what you're saying? 0 minus 15, because that's 25 to get to it. I hope so, because if so, that's good. That's all we needed to know. I just didn't know how we calculate that distance. But that's because this is... Oh, this is, yeah. This is the displacement of going at that acceleration. Okay, yeah. Okay, that's good. That's good. And then we have the minus 15, 10. That's already there for some reason. And at 5 seconds. Okay, so this should line up now. It didn't. Did it? No, stop doing that. At 5 seconds, we should be exactly on 10. We kind of are. I think this might be wrong now. So we're going at, where is this? This is 10, 15, yeah, it needs to be 6.67. That's why. But I think that displacement has fixed it for us. I was just wondering, I just didn't think which chart it's going to be on, but that's okay. That's solved now. But this, yeah, we had to go back to this displacement and line it up with it. And it's funny because when I first saw this, I was like, this looks really familiar. It looks like this. But I'm totally blanking that this is distance and this is the accelerator. You know, this is the speed that you reach. Okay, that's nice. Laurel Clark, she's one of the 2 female astronauts who died in the Space Shuttle Columbia disaster in 2003. Doctoral student in medicine, she specialized in submarine rescue, then became a naval flight surgeon before becoming an astronaut. During her final space flight, she had to perform around 80 scientific experiments related to biology and growth in weightless conditions like a real space farmer. Okay, last one of this area, and now that we understand that, hopefully we will be able to do this one a lot easier. Seems to me like what we would want... Oh my god, we've got a displacement and a velocity. Do we actually need to do anything with it? Because what I see here is a black hole that's at -10, -10. And because that's a radius of 20, radius is 20, and we're going at 10, that's going to be a strength of 5. There we go, strength of 5, and that's if we're going 10. We can't initially go 10 once again. We're starting at this initial position, that's the problem. So what we want to do is very simply start accelerating whichever direction, and then we'll just teleport ourselves. We'll just displace ourselves. And the delta velocity. Okay. Okay. So we want to like move along here and then displace ourselves up here to just like... That's fine. So what do we want to do? We want to reach 10 again. Let's reach 10 again. 10 seems good. So in 5 seconds. And then if we do this, speed of 10 with a radius of 20, 5 seconds again. That's strength of 5, but then 10 with a radius of 20 is 12 seconds. So we can't do that. We've got to do it 15. We've got to be at speed of 15 to do it in because the radius is so big. So speed of 15 is what we need. And then if we're 15, 20, that's 11.25 we need this to be. Okay. And we need to get to 15, don't forget. So, what happened? No, go back. Want to get to 15. So, where do we get to 15 here? You don't. But what you can do is increase the delta velocity and when we displace it. So why don't we spend... This is going to take 8 seconds to do this loop. It's got 8.3 seconds. So we need to get to 15 very fast. So that's 8 seconds. We need to do it in like 1 second. In 1 second, we get to 10. Alright, so in 1 second, we accelerate -10. 1 second. And then, at 1 second, we displace from 10-1 from... We've moved 5 only. So we're going to move from -5, 5, 0 to -10, 10. So we're going to go a further -5 and 10. And at 1 second, we're also going to increase our velocity by a further 5. Because it's going to be from 10 to 15, and we need to be going 15 and to get around this fast enough, right? That seems fine. Let's try it out. So we should move here, teleport here, and then be fine to go around here in time. And then we just go, wee, keep going, yay. Awesome, my god, it's full of stars achievement. That is all levels completed. We did it. We've done it. We've done it. Kalpana Chawla. She is one of 2 female astronauts who died in the Space Shuttle Columbia in 2000. Determined and ambitious, she refused to give up her dreams despite the many people who stood in her way because she was a woman. Born in a small town in India, she obtained her doctorate in engineering in 1988, then became an astronaut in 1994. She reportedly said, "The path from dreams to success does exist. May you have the vision to find it, the courage to get to it, and the perseverance to follow it." Horrible. Really sad. Really, really sad. We're just going to read these last few things, and I think that's pretty much it. So, Sea of Crises we already read, but let me just go over it again. Here's the Sea of Crises, the most easily spotted lunar sea. It's also the first sea to appear during a lunation, that's to say, during the first crescent. Luna 23. Luna 23 made a soft landing on November 6, 1974, but ultimately tipped over onto its side. It was therefore unable to collect a soil sample as Luna 16 and 20 had previously done. In 2012, the American Lunar Reconnaissance Orbiter took a photo of Luna 23, in which the probe can be seen stretched out on one of its sides. Aww. Luna 24. Luna 24 was the last lunar probe of the lunar series to return to Earth with a sample of lunar soil. It made its landing on the moon in August 18, 1976. With a robotic arm and a drill, it dug 2 meters into the ground. Luna 24 collected 170 grams of lunar soil in a small return capsule. It landed in Siberia on August 22nd, 1976. Let's do this end of the story first, and then we'll read the rest of the people. Because we've skipped the story, basically, but that's totally fine. You never gave up, and now you're ready for takeoff. Not yet. Where are you? Look down. Hello. Oh, that's you? Yes, it's my disguise. Oh, wow. Is everything okay? Yeah, definitely. All okay. So okay. Good to meet you. Likewise. I'm so excited you have no idea. I think I have some idea. All right, we ready for takeoff? Let me run all the tests. Check, check. 100%. Check, check, check. 100%. 99.9%. Oh, no, I forgot something. To repair your car before our departure. That would be nice. That's what we were here for. Oh, mama. Real nice. Oh, damn. Wow, brand new car. But does that mean you could have fixed my car right from the start? Maybe. I need one last thing. If I tell you that the moon's gravitational acceleration is about 0.5 meters per second at 3,000 kilometers from its center, can you tell me what speed we'll need to start orbiting around the moon? Are you kidding me? What? 0.5 at 3,000? What speed we'll need to start orbiting around the moon? And there's only one. A kilometer or a second? 1 kilometer a second. 1,000 kilometers a second. If I tell you that the moon, if we half it, okay. So if we multiply it, it's about 1,500, right? If I tell you moon's gravitational acceleration, let's go. It's about 1 kilometer a second. Because if we go 1,000, we're gonna shoot off. Isn't that what we want to do, though? We don't want to be on the moon. We want to shoot off of the moon. I had to use the centripetal acceleration equation. A equals v squared over r and isolate v. I want to get off of here, though. You almost got me, but I'm very proud of you. I like the sound a lot. Let's go. Let's get out of here. Can we get a countdown? What? This is you can see now why I skipped the story, and I'm sure you're not upset by it. You know how space stations do a countdown before we blast off. Why not? Ready? 3, 2, 1. Blast off! In my new car. We don't want to orbit the moon, though. We don't want to orbit the moon. We want to shoot out of orbit, right? Isn't that the point?
You're very exceptionary. No
I dedicate this game to my son, Maxence. Hello, Maxence. Hello, Max. Your passion for video games, your curiosity, and your sense of humor are a great source of inspiration to me. I love you. That is lovely. Concept, science stuff, game and level design, Mr. Sir Eric LaFlamme. Programming, Eric LaFlamme. And Dominic Gendron. Alright. We did it, guys. We got there. Oh, narrative. Narrative designer. We don't want that. We don't want the narrative. We just want the science stuff. Design consultant, Waco Factory. The design, like, it looks nice, but the pages, some of the pages when you swap between them and it shifts a little bit, that stuff gets to me. And when the scientists come up as well, and the arrows look weird and the cross looks weird, and I work with software every day. I work with software, and I work a lot with design as well. So obviously I'm going to be picky, but yeah, that stuff gets to me. Like, shouldn't shift like that, and the little arrows look really awful. They're like inside a box, but they're almost touching the box, so there's no padding around them, and I'm like, ah. But it all worked. And that's what really mattered. Boom, boom, ba-dum, ba-dum, boom. Oh, this is nice. This is what now we can just Now we just lean back. Special thanks. Maxon Slavflam, there he is again. Oh yeah, now we just take it easy. We're done. We're done. Where's Space Tow Truck 2? Send me the DLC, the insanely difficult DLC that you spoke about, Mr. Laflam. Now we're waiting for you. We're waiting for you. Woo! Emojis. Okay. I didn't see any actual emojis though. It was just like text emojis. It was like ASCII emojis. So I don't know why. Okay. Bibliography. The Women of the Moon, Oxford University. Okay, that's just all of his sources, I suppose, for the information that we read. That was so cool, right? That was so cool. Learning about the different scientists and what they managed to accomplish. And it kind of actually came full circle because it was just, at the beginning, it was about creators on the moon and scientists that they were dedicated to. But then, after that, it actually started to be about also astronauts as well. And pretty awesome, really awesome. Thank you for your perseverance and your curiosity. Oh, well, I tell you what, even though everybody's going to hate me because I'm a big puzzle fan, and not everybody is, I'm going to be for being there until the end. And I'm going to be buying this game for people's birthdays. When I see somebody that doesn't own this game on Steam and it's their birthday pops up, bang, this is the game that you're getting now, because this needs to be shared around. This is cool, really cool. Anybody can enjoy this. I love puzzle games so much, and having puzzle games where I'm learning something, I don't know, it's deeply interesting. We've learned about acceleration and gravity and just stuff that you think that you come away from school knowing, you know? You come away from school, oh, you should know all of this stuff, but you don't really, because I know it's a little bit more advanced, but you do lose a lot of that if you don't use it every day. And I do like maths and science, but I do find myself, you know, I don't know, you forget even just bits of trivia that you're forgetting over time. And it's really nice to play something that kind of throws you back into that world again, the academic world. It's been great. It's been a lot of fun. So I'm going to write my review of this. That was obviously my last video of Space Tow Truck. It's been a long trek. I think that was the 9th video, maybe the 8th. And it's been challenging. Ups and downs, very silly mistakes. But then also some serious crushing of certain levels as well, just absolutely dominating them. But I have had a marvelous time. I will make sure this game, by the way, has no Metacritic right now, so my review is probably going to be the first review on Metacritic. It also seems to not be super popular in Steam, and usually I don't put my reviews on Steam also, but I think I'll have to do that just to try and get some traction around it. But this is great. This is fantastic. I would highly recommend you try it for yourself if you like the look of it. You kind of know a lot of the solutions, but I bet you're not going to memorize them all. You could try and do it for yourself, and I'm sure you'll have to think and it'll stump you. But this is one that I'm going to be gifting to a lot of people, no doubt. Thank you very much for watching, and see you next time. Bye.